Alright, so in this video we're going to talk about shifted conics, and it's really important to mention that we are coming off of our conversations about conics more generally, so we already have a sense of how parabolas, ellipses, and hyperbolas work. However, up until this moment, all of the conics that we have looked at so far have been ones that were centered at the origin, or in the case of parabolas, had their vertex at the origin. So for example, one form of the equation of the parabola would be something like x squared is equal to 4py, right? So this would be a parabola that opens vertically, and its vertex would be at the origin, and depending on the size of P, it would be more open or less open. The directrix would be impacted by the size of P, but we knew right away that the vertex was at the origin. The parabola could also look like y squared is equal to 4px. Same thing. This would be a parabola that opens side to side, and it would be influenced in terms of its width by the size of P. The directrix would be different depending on P, but the vertex would be at the origin. Ellipses, same idea, right? So with ellipses, we either have x squared over a squared plus y squared over b squared is equal to 1. So in this instance, so you remember A dictates the length of the major axis. The fact that A is located in the X column, I guess we could say, indicates that in this example, the major axis is horizontal, and this is an ellipse where everything is centered at the origin. So the vertices are symmetric about the origin, the foci are symmetric about the origin, everything is centered about the origin. The other alternative for ellipses is that the major axis is vertical, and nothing really changes, right? It's just that now the larger denominator is under y, and again, everything is symmetric about the origin. For hyperbolas, exactly the same thing. So you could have a vertically oriented or a horizontally oriented hyperbola. So this is an example, since A is located under X, this is an example of a horizontally oriented hyperbola, but everything is centered about the origin. By that same token, here is a vertically oriented hyperbola. And, you know, we can talk about its asymptotes, we can talk about its foci, but the point is everything is centered about the origin. That is what we have done up until now. So the natural next question is, okay, well, what if the center is not the origin? What if the vertex is not the origin? And what's really important is that we have come here after all this time having talked about transformations. So you know something about how to achieve the shifting of the center. So I'm putting center in quotes here because we don't mean center in the same way that we mean of a circle, and we really mean center or vertex, but I just want to be concise, right? So the idea is that it's very much the same as it was with transformations. The only thing to keep in mind is transformations were dictated by, we did them in the context of functions, right? So we had inputs, we had outputs, it was a function. That's how we thought about them. Conics are not functions, okay? No conic can be written as a single function of either x or y. So we don't quite think of the shifts in the conics the same way as we thought about the shifts in functions. So I'm going to write out the possible shifts and how they work, and we'll kind of check in to see where it's a lot like transformations and where it's a little bit different. So the main idea that we are comfortable with is that when we start adding or subtracting something from x, and let me make this a little bit more clear here. So we're replacing x replaced by x minus h. So we know that when we add or subtract something from x, that's going to be a horizontal shift. And for this piece, it's going to feel a lot like transformation. So replacing x with x minus h, that's a shift to the right. H units. And replacing x with x plus h, that's a shift to the left. H units. So here it's completely in line with the way that we think about transformations. The difference comes with the y. So when we replace y with y minus h, we're kind of accustomed of thinking of this as a shift downward, but that's because in the context of functions, that was an output. So the function acted on the thing first, and then we did the subtraction. Here, it's not a function, so it's actually going to be the same effect as we have with horizontal shifts. So replacing y with y minus h is a shift up h units. And finally, replacing y with y plus h, that's a shift down. Also h units. So in this video, I'm just going to walk us through one example of a shifted ellipse, actually. And in this instance, we're actually going to be given some information about the ellipse, in particular its vertices, and we're going to talk through setting up its equations. In the next video, I will actually do one or two examples where we walk through if I'm given the equation of a conic, but I'm not told what conic it is. How do I A, determine what conic it is, and B, figure out questions like its center, vertices, and whatever other appropriate features, right? Okay, so let me pull up our example here. So the example that I wanted to go over with you is this. An ellipse has vertices -1, -4, and -1, 6, and its foci are -1, -3, and -1, 5. And what we're asked to do here is to find its equation. So I hope that you are sort of carrying this over from the general conversation about conics, that we are going to be looking for things like, well, A and B, really. That's what we're here for. Does A go under the Y or go under the X? That depends on whether the ellipse is oriented horizontally or vertically, and so on. So you're not going to be surprised for me to tell you that let's start by plotting these points and getting a picture going. I am never, ever, ever going to let us forget the importance of drawing pictures. Even if it's not a super, super thorough or detailed picture, a picture is always, always important. Okay, so our vertices are -1, -4. So let's call this V1 and -1, 6. Okay, so we'll call this V2. If you like to label these points, you can. I always worry that too much labeling makes the graph claustrophobic and difficult to read, but this seems to be okay. So the first thing that we see right away, right, you can connect these two with a dotted line if it's helpful. Right away we see that the major axis is vertical. Remember, the vertices are always on the major axis. And since these two vertices are on a vertical line, on the same vertical line, we know that the major axis is vertical. Since we're talking about the major axis, let's go ahead and talk about its length. So you can see that if you start at one of the vertices and then count the number of units to get down to the second one, that's 10 units total, 6 to get down to the x-axis, 4 more to get down to the second vertex. Another way to think about that is that since they're on a vertical line, the length of it is going to be dictated entirely by the y-coordinates, so we simply subtract the smaller y-coordinate from the larger one. So 6 minus -4 is 10. Now remember, the length of the major axis is 2a. So that means that 2a is equal to 10, and already we're on track to start thinking about the equation. So we know that a is equal to 5. So I'm sort of building up a little collection of information down below. The next thing we need to know is the center, or at least that's the part that we're going to talk about next. You could also talk about the foci next, but I think the center is the appropriate thing to discuss next. So the center is the middle, or the midpoint, of the vertices. You could find the midpoint by averaging the coordinates. So you could take the average of the x-coordinates and the average of the y-coordinates, and that would give you your midpoint. Personally, in this case, and in most cases, I think a picture is far more efficient and actually more illuminating. So we know that half of the length of the major axis is 5, so we can just start on one of the vertices and then go towards the center 5 units. So -1, 6, 1, 2, 3, 4, 5. So here is my center. So you can see this point is the point -1, 1, and it is both 5 units from the second vertex and 5 units from the first vertex. So it's halfway, and so the center is -1, 1. Now remember, we spent a little bit of time talking about this at the beginning. Up until now, all of the conics we have looked at have been centered at the origin. So if this is my center, oops, wanted to do that in red, -1, 1. C for center. We can see that starting at the origin, that will be a shift left 1 unit and a shift up 1 unit. And that's going to be really important when we start talking about the equation. We're going to look at this. We're going to say, oh, hey, we shifted left by 1 unit. So that's going to mean replace x with x plus 1. And we shifted up 1 unit. So we're going to replace y with y minus 1. Okay? So we're going to keep that in mind for later. So the next thing we're going to talk about is we're going to talk about the foci. Okay? So I'm going to go ahead and plot the foci. We'll use some nice third color. So the foci are -1, 5. So let's call this C1. Or, you know what, let's call it F1 so as not to get confusing with the C's. So F1 is one focus, and the other focus is -1, -3. And you know what, let's call this one F1 and this one F2 to sort of be consistent with our labeling. Okay? So remember, the distance from either focus to the center, that's our C. So since, let's label nicely, even if it means our picture is a little bit claustrophobic, since our center is the point -1, 1, And our foci are the points -1, -3, and -1, 5. We can see that the distance from the center to either focus is 4. So that tells us that C is equal to 4. And this is where we're going to recall that C squared is A squared minus B squared. Okay, so this comes from our conversation about ellipses long before we started talking about shifted conics. Okay, so given the fact that we know what A is 5, and given the fact that we know that the relationship between A, B, and C, we can say that C squared is equal to A squared minus B squared. Okay, so 16 is 25 minus B squared. Oh, so B squared is 9, so B is 3. Okay, so at this point we know A, we know B, we know that the major axis is vertical, so that means that Y is the one that gets the bigger denominator, and we know our shift, which means we know what to replace with what. So we're ready for the equation. So let's go ahead and wrap this up. The equation is going to be y minus 1 squared over 25, or 5 squared, plus x plus 1 squared over 9, or 3 squared, is equal to 1. So I will finish this video by saying shifted conics are conics. Everything that we've come to know about conics, how to find them, what they are, what properties they have, is preserved with shifted conics. It's just now we have this extra layer where we have to think about, okay, where is the center and what shifts does that imply? Never is it going to be more helpful to draw pictures than when you're dealing with shifted conics. I hope you found this helpful. As always, post in the discussion forums with questions. And that's the end of this lesson.